So first up in our lightning round talk is Paul Hayne, and he'll be discussing polar night vision, thermal infrared imaging at the lunar surface.
Okay, thanks, Ariel. Okay, so this is a short presentation on the utility and science applications of thermal infrared imaging at the lunar surface for surface science. And I wanted to acknowledge all my co-authors here who are also members of the Lunar Compact Infrared Imaging System team, which I'll talk about in a second. So next slide. So the context for this, as previous speakers have touched upon, is the Diviner radiometer instrument. So we've been flying Diviner on LRO in lunar orbit for upwards of a decade now. So we've learned a lot about the lunar surface thermal environments and the subsurface as well. This is at a scale that is resolvable from orbit of 250 meters per pixel by Diviner. And so the colorful plot there shows an example of a map of the South Polar region near the L-Cross impact site, where you can clearly see all of these beautiful PSRs and cold traps at a scale of 250 meters or so, or larger. So the question is, what's going on down on the surface at smaller scales? And we have some insights into this, both from Diviner and from modeling. So the first point is that the thermal gradients on the surface are extremely large, so hundreds of degrees per centimeter. And that's just due to the thermally insulating properties of the regolith. Surface roughness and therefore shadowing also increase at smaller scales, and that's shown in the upper right panel, where you can see visually the roughness increasing as you go from a kilometer down to a centimeter scale, and that's important for creating these cold regions. We also know that the smallest cold trap is about a centimeter across, so building on Tyler Powell's presentation earlier. We also have a modeling paper that's coming out soon that shows that that's about the scale of the smallest cold trap, is about a centimeter. So that's a scale to keep in mind. Then also roughness. This is an important point that extends beyond thermal considerations and ice itself, but roughness contaminates both diviner data and near-infrared spectra, which is important for detecting both H2O and OH on the surface. That 3-micron band gets contaminated by emission from this rough surface. Next slide. So we designed the Lunar Compact Infrared Imaging System to get down on the surface and resolve some of these uncertainties on the small scale temperature distribution on the surface, as well as the small scale composition and mineralogy. So this instrument is based on the Cirrus CubeSat instrument, which is currently in Earth orbit. It's a radiometer featuring 4 different infrared bands from 7 to 14 microns. You can see the specification.
So, 2 minutes.
Thank you. The critical thing is that we can resolve down to scales smaller than a centimeter within a few meters of the lander, and then extending the field of view all the way out to the horizon. We also have a rotation stage that allows us to build up panoramic images from the landing site. Next slide, please. So the science objectives flow down directly from some of the high priority science from both the SCEM report and the strategic knowledge gaps from HEO. You can read them here. Next slide. I'm going to focus on this last one to make a point about what can be done from the surface with thermal infrared imaging related to volatiles, since that's the topic of discussion here. Next slide. So looking into the future, of course, we can anticipate more of this kind of thermal infrared imaging, but I'm also going to talk about something else. So next slide. So what could we do with thermal infrared imaging from the surface if also coupled to mobility? So an astronaut could carry a thermal infrared camera like L-Cirrus on the surface and rapidly identify hazards like rocks and loose soil. Also assess the geology to make quick decisions about what to investigate in a limited amount of time during a traverse. And then importantly for this discussion, also identify cold traps. Imagine being able to just look out and see where the cold
30 seconds
were.
Yep.
Slide.
Yep.
So the point I want to make here is that before we can follow the water per the NASA directive, we need to find the cold. And As Tyler pointed out earlier, the cold traps span a wide range of spatial scales, and so we really need to get down on the surface and use thermal infrared imaging to find them. Thank you.